In a previous video, we introduced the concept of the complex conjugate. In this video, we will go over the properties of the complex conjugate. Recall that if a complex number z equals a plus bi, then the complex conjugate of z, written as z bar, is equal to a minus bi. So the sign before the complex part is inverted and everything else stays the same. So the first property we're going to prove is z1 conjugate conjugate is equal to z1. This basically just means that if we have a complex number z1 and we take the conjugate, and then we take the conjugate again, we just end up with the original number z1. This intuitively makes sense because the conjugate inverts the sign before the complex part, so if we invert the sign twice, we end up with the same sign that we started with. So here's how we prove this. Suppose z1 is equal to a plus bi. Then z1 conjugate and conjugate again is equal to a plus bi conjugate, and then we conjugate this expression again. The expression inside the brackets is a minus bi, since the conjugate of a plus bi is a minus bi, and the second conjugate stays the same. A minus bi conjugate is just equal to a plus bi, since we have to invert the sign before the imaginary part, so this is just equal to a plus bi. And we've defined earlier that z1 is equal to a plus bi, so this is just equal to z1. So we have confirmed that z1 conjugate conjugate is just equal to z1. The property I'll go over next is the conjugate of z1 plus z2 is equal to z1 conjugate plus z2 conjugate. This basically means if you sum two complex numbers and then take the conjugate of the result, it's the same as taking the conjugate of the two complex numbers individually, then summing the results. So here's how we do the proof. We write z1 plus z2 conjugate, and this is just equal to a plus bi plus c plus di conjugate. And this is because we defined z1 equals a plus bi and z2 equals c plus di. If we sum the real and imaginary parts of the complex number inside the conjugate, this is just equal to a plus c plus b plus d multiplied by I, and then all of this conjugate. This expression is just equal to a plus c minus parentheses b plus d times I, since when we take the conjugate of this complex number, we need to invert the sign before the imaginary part. Well, the imaginary part was parentheses b plus d, so this becomes negative parentheses b plus d for the imaginary part for this new complex number. If we apply the distributive property, this is equal to a plus c minus bi minus di, and this is equal to parentheses a minus bi plus parentheses c minus di, and this is great because we can see that a minus bi is just z1 conjugate and c minus di is just z2 conjugate. So this is equal to z1 conjugate plus z2 conjugate. So we have confirmed that z1 plus z2 conjugate is just equal to z1 conjugate plus z2 conjugate. The next property we'll go through is z1 minus z2 conjugate equals z1 conjugate minus z2 conjugate. This is similar to the previous property except with subtraction, and the proof is quite similar. So here's what we do. We start with z1 minus z2 conjugate, and this is just equal to a plus bi minus parentheses c plus di conjugate. If we apply the distributive property, this is just equal to a plus bi minus c minus di conjugate. We can rewrite this as a minus c plus b minus d times I if we combine the real and imaginary parts, and then all of this is under the conjugate. And if we take the conjugate of this expression, the plus sign before the imaginary part becomes a negative sign. So this is just equal to a minus c minus parentheses b minus d times I. If we expand out this expression again, we can rewrite this as a minus c minus bi plus di, and we can group up the terms and rewrite this as a minus bi plus negative c plus di. If we factor out a negative 1 out of the second parentheses, we can rewrite the expression as a minus bi minus c minus di, and this is the form that we want, since a minus bi is just the conjugate of z1 and c minus di is just the conjugate of z2, so this is equal to z1 conjugate minus z2 conjugate, which means we have confirmed that z1 minus z2 conjugate is just equal to z1 conjugate minus z2 conjugate. The next property is that z1 times z2 conjugate is just equal to z1 conjugate times z2 conjugate. So this basically means if we have a product, we can either multiply the two complex numbers together and then take the conjugate, or we can take the conjugate of the two numbers separately and then multiply the result. And in either case, the result is the same. So we start off with z1, z2 conjugate, and this is equal to a plus bi times c plus di conjugate. If we apply the distributive property, this is just equal to ac plus adi plus bci plus bdi squared conjugate. I squared is equal to -1, so this is just equal to ac plus adi plus bci minus bd conjugate. If we group up the real and imaginary parts, we can rewrite this as ac minus bd plus parentheses ad plus bc times I, and this is all under the conjugate. If we want to find the conjugate of this complex number, we need to invert the sign before the imaginary part. So this is equal to ac minus bd minus parentheses ad plus bc times I. If we expand out the terms, this is equal to ac minus bd minus adi minus bci. So now we need to factor this expression, and we're going to apply a little trick. We know that I squared is equal to -1, so we should rewrite the second term as bdi squared instead of -bd. So this entire expression just becomes ac plus bdi squared minus adi minus bci. So we can factor this by putting the first and third terms in a group and the second and fourth terms in the other group. So this becomes parentheses ac minus adi plus parentheses bdi squared minus bci. If we factor out an a from both terms in the first group, this becomes a times parentheses c minus di. And if we factor out a bi from both terms in the second group, this becomes bi times parentheses di minus c. This is just equal to a times parentheses c minus di minus bi times parentheses c minus di, and what we've done here is we have factored out a -1 from the second parentheses. And if we continue from here, we can factor this as a minus bi times parentheses c minus di, and notice how a minus bi is just z1 conjugate and c minus di is just z2 conjugate. So this is just equal to z1 conjugate times z2 conjugate. So we have confirmed that z1 z2 conjugate is just equal to z1 conjugate times z2 conjugate. A similar property also applies to division. So z1 over z2 conjugate is equal to z1 conjugate over z2 conjugate. This means dividing z1 by z2 and then taking the conjugate of the result is equivalent to taking the conjugates of z1 and z2 separately and then dividing z1 conjugate by z2 conjugate. So here's what we do. We first consider the left-hand side, z1 over z2, and all of this is under the conjugate, and this is just equal to a plus bi over c plus di, all under the conjugate. To simplify the complex number inside the brackets, we should multiply both the numerator and denominator by the complex conjugate of the denominator, which is c minus di. So this becomes a plus bi times c minus di over c plus di times c minus di. And then all of this is under the complex conjugate. If we expand this expression, this becomes ac minus adi plus bci minus bdi squared, and the denominator becomes c squared minus d squared I squared if we apply the difference of squares formula, and all of this is under the complex conjugate. I squared equals -1, so we can rewrite the expression as ac minus adi plus bci plus bd, and what we've done is we've replaced the I squared with -1, so negative bd times -1 is just positive bd. And the denominator becomes c squared plus d squared, since if we replace I squared with -1, then negative d squared times -1 is just positive d squared. And all of this is under the conjugate. If we combine the real and imaginary parts for the complex number inside the brackets, this becomes AC plus BD over C squared plus D squared plus parentheses negative AD plus BC over C squared plus D squared times I. All of this is under the conjugate, and to get rid of the conjugate, we just need to invert the sign before the imaginary part. So this is just equal to AC plus BD over C squared plus D squared minus parentheses negative AD plus BC over C squared plus D squared, and this is multiplied by I. If we distribute the negative sign into the brackets, this is equal to AC plus BD over C squared plus D squared plus AD minus BC over C squared plus D squared multiplied by I. So now what we need to do is we need to consider the right-hand side, Z1 conjugate over Z2 conjugate. This is just equal to A minus BI over C minus DI. We can simplify this by multiplying the fraction throughout by C plus DI, which is the conjugate of the denominator. So this becomes A minus BI times C plus DI over C minus DI times C plus DI. If we apply the distributive property, this is just the same as before, and this is just AC plus ADI minus BCI minus BDI squared divided by C squared minus D squared I squared. And as we know, I squared is equal to -1. So this is just equal to AC plus ADI minus BCI plus BD over C squared plus D squared. Well, if we separate out the real and imaginary parts, this is just AC plus BD divided by C squared plus D squared plus parentheses AD minus BC over C squared plus D squared times I. Well, this expression is just the same as the expression that we found for Z1 over Z2 conjugate, which was right over here, AC plus BD over C squared plus D squared plus parentheses AD minus BC over C squared plus D squared times I. So Z1 over Z2 conjugate is equal to this expression, and then we also know that Z1 conjugate over Z2 conjugate is also equal to the exact same expression, and therefore we can confirm that Z1 over Z2 conjugate is just equal to Z1 conjugate over Z2 conjugate. So there's another property that comes as a consequence of the multiplication property, and that's Z1 to the power of n conjugate is equal to Z1 conjugate, all raised to the power of n, for all integer values of n. It's very important that the exponent n is an integer, because when n is not an integer, the rule does not hold in general. There's a formal proof of this using induction, but I'm not going to get into that here and just informally show why this works. To prove this, we're going to need to use the property Z1 Z2 conjugate is equal to Z1 conjugate times Z2 conjugate, which we proved earlier. So let's first consider the case where n is greater than or equal to 1. If we start with Z1 to the power of n, all under the conjugate, we can rewrite the expression inside the conjugate as Z1 times Z1 to the power of n minus 1, and then this is all under the conjugate. What we can do is we can use the property Z1 times Z2 conjugate equals Z1 conjugate times Z2 conjugate to rewrite this as Z1 under the conjugate times Z1 to the power of n minus 1 under the conjugate. So we can do a similar thing for the Z1 to the n minus 1 term and rewrite it as Z1 times Z1 to the n minus 2. We can use the multiplication property again and then split that into Z1 conjugate times Z1 to the power of n minus 2, all under the conjugate. Notice how each time we do this, the exponent in the term with the n in the exponent decreases by 1, and we end up with another Z1 conjugate term. So if we continue this pattern, we will eventually end up with n of these Z1 conjugate terms all multiplied by each other in a product. Well, this is just the same thing as Z1 conjugate all to the power of n. So we've confirmed that z1 to the power of n conjugate is just equal to z1 conjugate all raised to the power of n. This is kind of an informal proof, but the idea is to repeatedly apply the property z1 z2 conjugate equals z1 conjugate times z2 conjugate until you end up with the z1 conjugate multiplied by itself n times. Notice how this only works when n is a positive integer. So if we consider the case where n equals 0, well, there's only one thing to consider, and that's just z1 to the power of 0 under the conjugate. Well, z1 to the power of 0 is just equal to 1, since any complex number to the power of 0 is equal to 1, and this is under the conjugate. And the conjugate of 1 is just equal to 1, because there's no imaginary part to consider. So you can think of 1 as just 1 plus 0i. Well, if you take the conjugate of that, that's just equal to 1 minus 0i, and that's still equal to 1. On the other hand, z1 conjugate all raised to the power of 0 is just equal to 1, since z1 conjugate is definitely a complex number, and any complex number raised to the power of 0 is equal to 1. So z1 to the power of 0 conjugate is equal to 1, and z1 conjugate all raised to the power of 0 is also equal to 1. So we've confirmed that z1 to the power of 0 under the conjugate is just equal to z1 conjugate all raised to the power of 0. So this property holds when n equals 0. So let's consider the case when n is negative, which means that n is less than or equal to negative 1. To prove that this property holds for negative integer values of n, we're going to have to use two other properties. We need to use the exponent law, z to the power of negative n equals 1 over z to the power of n, which holds true when the base z is a complex number, and the division rule, z1 over z2, all under the conjugate, equals z1 conjugate over z2 conjugate. So if we start with z to the power of n, all under the conjugate, we can rewrite this as 1 over z to the power of negative n, all under the conjugate, using the exponent law. And using the division rule, which we proved earlier, this can be rewritten as 1 conjugate over z to the power of negative n, all under the conjugate. The conjugate of 1 is just 1, so the numerator is just equal to 1. And since n is a negative integer, negative n is positive. We've already shown earlier that the property z to the power of n all under the conjugate equals z conjugate all to the power of n holds for all positive integer values. And since, in this case, negative n is a positive integer, we can rewrite z to the power of negative n all under the conjugate as z conjugate all raised to the power of negative n. We can now apply the exponent law again to rewrite this as z conjugate all raised to the power of n. So we have confirmed that for n less than or equal to negative 1, z to the power of n all under the conjugate is just equal to z conjugate all raised to the power of n. So we have proved that z to the power of n all under the conjugate is equal to z conjugate all to the power of n for integer cases where n is greater than or equal to 1, n equals 0, and n is less than or equal to negative 1, which means the property holds for all integer values of n. So the next property we're going to prove is the absolute value of z1 is equal to the absolute value of z1 conjugate. And recall that the definition of the absolute value of a complex number is that the absolute value of z1 is equal to the square root of a squared plus b squared. So if we start with the absolute value of z1, that's just equal to the square root of a squared plus b squared. And if we consider the absolute value of z1 conjugate, that's just equal to the absolute value of a minus bi, since the conjugate of z1 is just a minus bi. The absolute value of a minus bi is just equal to the square root of a squared plus negative b all squared, because if we look at the definition of the absolute value, it's just the real part squared plus the imaginary part squared, all under the square root. This is equal to the square root of a squared plus b squared, and notice how this is the same expression for the absolute value of z1. So the absolute value of z1 is equal to the square root of a squared plus b squared, and the absolute value of z1 conjugate is also equal to the square root of a squared plus b squared. So we can conclude that the absolute value of z1 is equal to the absolute value of z1 conjugate. The final property we're going to go over is z1 times z1 conjugate equals the absolute value of z1 all squared. So if we multiply a complex number by its conjugate, we just get the square of its absolute value. So suppose we start with z1 times z1 conjugate. This is just equal to a plus bi times a minus bi. This is equivalent to a squared minus b squared I squared if we use the difference of squares formula, and I squared equals -1, so this is just a squared plus b squared. Notice how the absolute value of z1 equals the square root of a squared plus b squared. This means if we square the absolute value of z1, we just end up with a squared plus b squared. This means a squared plus b squared equals the absolute value of z1 all squared. So we can conclude that z1 times z1 conjugate is just equal to the absolute value of z1 all squared. So to recap, here are all the properties of the complex conjugate that we went over in this video. If you take the conjugate of a complex number twice, the result is the original complex number. There is one for each of the 4 basic operations, as well as for exponentiation with integer exponents. There are also 2 properties of complex conjugates involving the absolute value.